We already started talking about zero force members just analytically in one of our last examples when we talked about the method of joints. And what you've seen there was actually a joint that looked something like this. So there was a hinge here. We cut through one member, another member, and another member. And I already told you that we had two parallel members. So two parallel members that were jointed by, and I purposely said that last time, by a random third one. This one here actually happens to be not random. It's actually perpendicular. But remember that for this case here, it's easier to see that any force that is acting perpendicular to this system cannot be resisted at this node because you cannot create equilibrium here. So let's say you pull on this member, it's not resisted up here. So therefore, you only have one force in one direction, and therefore you cannot create equilibrium. That means that this member here must be equal to 0. And therefore, this actually works for any scenario, not just for the perpendicular case, but I can have the very same scenario. So let me redraw the system here. And let me join a third one, which now is actually under an angle. And often students think, now it's under an angle. Now that it cannot be a zero force member anymore. But remember, we cut through the system here and here and here. And the red component here, or the one that is not parallel with the other two ones, actually has a vertical component and has a horizontal component, something we dealt with very early in this class. And so this vertical component here, it may go up, it may go down, it doesn't really matter, but because it cannot be balanced at this point. So there's nothing here on the top that can balance this or can counteract this. And therefore, this must be a zero force member. It doesn't matter what the angle is, it has to be a zero force member. The 90-degree angle is just a very special case, and you see that often in real life because it's easier to fabricate it that way and so on, and there's other reasons for that too. However, analytically, you will always find that this must be 0 because there's nothing to balance this. So, and I'm going to call this case 1 here. So, case 1. And the way I would write that down under case 1 here is I have two parallel members that are joined by a random third member. If that happens, the random third member must be 0. But not to worry, even if you don't see this in advance, you often get there analytically. Like it comes out when you write your sum of the forces at x and sum of the forces in the y direction at any node. This will always resolve itself. So if there's a case 1, you can already tell there will be a case 2. So let's write down the case 2 here on the other side. And what is the case 2? And that is when you have an external node, so that looks like this, and that is not loaded. So now I cut this one. So I have two external members, and the structure can continue here. Like there's whatever something is going on there. It doesn't really matter. I can maybe draw it like this. And it doesn't really matter what goes on there. The matter of the fact is that this is an external node that has no load on it. And so for now, I pretend there's a load on it. And if you have the load there, then you would probably see that the vertical component that is acting in this member could balance that. But remember, in this case, the second case only talks about the fact that it's an unloaded external node. So if that force is not here, there's no force here, then this one cannot balance it. And also this doesn't matter if this is horizontal or vertical, it's an unloaded external node has only two members acting on it. And if that's the case, you cannot have any load there. So let's draw another scenario here. So for example, let's say I have a node that looks like this. And who knows what else goes on in the structure. So maybe I have something that goes on like that. And whatever else happens there, we don't care about. All we care about is that I have an external node that is not loaded, right? And so that is our case number 2. So let's write that down. So case number 2 is 2 external members come together at an external node, which of course is necessary, otherwise it wouldn't be an external member. But this external node that is unloaded, or that is not loaded. So it doesn't carry any load. So those are my 2 cases, right? I have first the case number 1, which was discussed up here. Let's look at that again. So the case number 1 is 2 parallel members that are joined by a random third one. And case number 2 is any external 2 members that come together at one joint. And please note the word 2 here. So in fact, let's maybe highlight it. So here the word 2 is important, and external node, and not loaded. And since we're highlighting, let's also talk about the parallel members here that are joined by a random third one. So then the random third one must be 0. And you can use this now to pretty much analyze systems before you actually run any numbers. And this can become helpful, as you will see on the next page. So let's look at these systems here. And it's a very straightforward exercise. All we're asking you is to find all zero-force members before you even start your calculations. You can use these to practice calculating the method of sections or method of joints, but that is not the point here. Right now, we're trying to look at each of these systems and try to identify the zero-force members. So these systems all have zero-force members, and let's try to identify them. So I start here on the top left, and what I see here in node E is 2 parallel ones with a random third one joined. It actually is not random, it's 90 degrees, but the rule is random. And I have the very same effect here at node B. 2 parallel ones and the random third one. So what I can do, and the way I show this, is I cross these out. This is how you would show it on an exam, but for the next ones I just erase them so that you can see what is actually part of the structure. So let's look at this one here on the bottom. So here I have this case very often, and this will become very interesting because for the first time now you will see that this actually carries through. So here at node E I have 2 parallel forces, and there is a random third one that joins it. So now let me try to zoom in to do a better job here of showing this. So effectively member EC does not exist. So I can literally erase this, and that is how that would look like. And so now you see what's happening. It's actually such that now member CF is having the same condition. So now I have this structure here, these two parallel structural members are joined by a third one, and therefore I can erase that one as well. And so what I end up with is a structure that looks like this. And once again, now I have this condition at node F. I have 2 parallel members which are joined by a third one, and I can also erase that. And one more time I can do the same thing at node B, and I don't think I have to explain that anymore. It's the same concept. And now I'm effectively done. So believe it or not, this entire structure actually is just reduced to these 3 members that you see. So effectively we have a member AD, we have a member DG and a member AG. And that's all this structure needs. All the stuff in between would not participate in carrying the load. And you can always show that numerically as well. Let's move on to the next structure. Let's take the one here on the bottom. So now what do we have? We have here we have two parallel forces and a random third one, but be careful now, there actually is a load now. So this cannot go to 0, right? If this would go to 0, this node would just not be able to resist the 2 kilonewton that's acting on the structure. So here, be careful. So that is not a zero force member. However, here at node F, it is a zero force member for the reason that we have two parallel forces and a third one here that goes in that direction. So once again, I can just erase this. And there we go. And once I've done that, you already see that I have the same condition now at member D, or like I guess at node D, and member DG has to disappear. And so I'll do that real quick. So that now is gone as well. And do I have any other zero force members in here? I don't think so, right? So let's continue to look at it. Yeah, here I have parallel members with a third one joined, but I also have this force acting here. And so therefore that's not 0. Same is true here. And since that is true here, this one also cannot go to 0. So I'm done with that one. Let's look at the next structure. So this one here on the top, what do we have going on here? I would say we definitely have a zero force member here because parallel and an unloaded third one. So let me make that disappear. So that's gone now. Do I have another one? Yes, I do. And that's a little bit deceiving again. I actually have two more ones because here I have actually the second case that we discussed, and that is the external unloaded node here. So there's an external node unloaded, therefore this has to disappear as well. So that was the second case. So the way that looks like is like that. This would have not participated in any load carrying activities. And that is not the case at node J, as you see here. Why is that? Because there is actually a load acting on the system. But so now I'm done with this and I can move on to the next one. And that one looks a little bit scary initially, but maybe we can also reduce this. So which ones participate in a load carrying and which ones don't. Here, again, I have my parallel ones and the random third one. So let me erase that one. So that goes to 0. And I think that's it for this structure. Yes, this is it. Everything else. So don't get me wrong, there might be another zero force member, but none one that jumps into your eye and that you can immediately see. So last but not least, here we have the node D, and node D again has this condition where this has to go to 0. And now node B has the same condition, so that has to go to 0. And therefore the real structure that participates in the load carrying mechanism does look like this. And that concludes our zero force members. Let's take a look again. So on an exam or somewhere on paper, I probably would use this method to identify what is my zero force members. But here I was lucky enough to just erase it and to clearly show how the final structure looks like. But you should use this method to cross out the members and to really understand where those forces are 0. And with that said, we are done with the zero force members and we can now go into our method of sections and run some numbers.